Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep, and let's try to recall what we were studying in the previous session. We had began with the SRAM cell, and we saw what the structure of the SRAM cell looks like. At the heart of the SRAM cell, we saw consists of this cross-coupled inverter. The key factor why there is a memory effect in the SRAM cell is because in this cross-coupled inverter, the output of the final stage reinforces positively the input of the first stage. And therefore, we saw there will be two bistable elements or two bistable points in this kind of inverter. Either N1 and N2 can be 0 or 1 or 1 and 0. We were looking at another very interesting way or interesting perspective. We were trying to get an analogy to a physical system, and we saw that these bistable systems can be described as a W-shaped potential well consisting of a EB potential barrier, right? So this W-shaped potential well will have two stable states, state at 0 and state at 1. And the question that I had left you guys with was, what should be the barrier height of EB? Should it be very high or should it be very low? So if you think a little carefully about it, if the barrier height is too small, the problem with such a system will be it will not be very stable. That is because if the barrier height is too small, a little bit of energy applied to the ball in one of the stable states and it will jump to the next state, right? So having a very small barrier height is not really a good idea. So can we make the height of the barrier or the energy barrier too large? That too has its own set of problems. Please recall that what is interesting about any memory element is not that it is able to hold on to the states, but also you can modify the value. You can write the value. In this case, if the barrier height is too large, it will take me a lot of energy to transport this ball from state 0 to state 1 and vice versa. So, engineering of SRAM cells is all about controlling or managing this so-called metastable state so that the barrier height is not so large that it is difficult to write, but it is not too small that the systems become unstable. With this perspective, let us try to see why we have a memory effect in case of SRAM cells. We have memory effect in SRAM cells because of these cross-coupled inverters. Today, we will deepen our understanding of the same. To do that, we will look at the VTC characteristics of these two individual inverters and then combine them. So what is VTC? It stands for voltage transfer characteristics. Voltage transfer characteristics is the terminology that we use to indicate how the output of the inverter changes with the input. So first, let's consider inverter 1. For inverter 1, as we can see that the input is node N2 and therefore I have placed N2 on the x-axis, and the output is node N1 and therefore I have placed N1 in the y-axis. So as we change the value of the input, in this case node 2, when the node 2 is at 0, we see that the value at the output is VDD. Why is this happening? This is a fundamental in CMOS design, but it might be worthwhile to do a very quick recap. This is because of this very simple structure of the CMOS inverter. Just imagine if the input Vin is 0, the NMOS will be turned off, the PMOS will be turned on, and therefore there will be a direct path between VDD and Vout. That's why the PMOS is also called a pull-up resistor, because when it is active, the output is pulled to VDD. In the other case, when V in is 1, we see that the output is 0. This is because when V in is 1, the PMOS will be turned off, the NMOS will be turned on, and naturally there will be a direct path between the V out and the ground, and that is why the NMOS is called the pull down transistor. With this very simple structure, you are able to get an inverter characteristics. An important thing to note in this inverter characteristics is that it is not an abrupt transition. The transition from the first stable state 0 1 to 1 0 is not abrupt. There is a finite slope, and this is indicated by the gain of the transistor. The gain of the inverter. The gain of the inverter, which is actually determined by the subthreshold swing of the individual transistors, is finite, and this is the characteristics of a real CMOS inverter. Okay, so once we have understood how inverter 1 behaves, let us see how inverter 2 is behaving. Please see that in inverter 2, which has been color coded with blue color, the input is storage node N1 and the output is storage node N2. So that's why in the x-axis we have indicated N1 and in the y-axis we have indicated N2. It has the exact similar characteristics as inverter 1, but only the difference is that the x and y axis have been flipped because the input of inverter 1 is the output of inverter 2 and vice versa. Okay, so this is very simple. When we decouple N1 and inverter 1 and inverter 2, their individual VTC characteristics looks like what we have plotted using these red and blue curves. Now what happens when we combine them, or in this case what happens when we cross couple them? Please recall the meaning of cross coupling is inverter 2 output is now connected to the input of inverter 1 and vice versa. Okay, so what will happen? So for understanding this, we will copy paste whatever was there in the characteristics of inverter 2 as it is. So we, as you can see, the combined characteristics, we choose the x-axis to be N1. So one of the branches will look absolutely identical to the inverter 2. What will happen to the second branch? For this, what we need to do is the red curve will not be completely overlapped. This is because the axes have flipped. The input and output axes have been flipped. So that has to be reflected. If you want to plot both the characteristics of inverter 1 and inverter 2 in the same graph, you will have to flip the axes of inverter 1, and this is what I have done. So I have flipped and rotated and placed the characteristics of inverter 1. And this is where we see this very beautiful looking butterfly characteristics. See, it looks like a butterfly. It looks like two wings of the butterfly. So these are called butterfly loops or butterfly hysteresis. What is the meaning of hysteresis? Hysteresis refers to any kind of characteristics where a particular input value need not have a single output. As you can see, a particular input N1 can have this value or it can have this value. In other words, in hysteresis, it is not necessary if I go from 0 to VDD, the path that I may follow is the same that I will follow back when I return from VDD to 0. This is another way of looking at hysteresis. But now we are yet to answer the question. This looks like a very pretty curve with hysteresis, but why does it give you the memory effect? Or why does it give you the so-called positive regenerative feedback? That is what we will see in the next slide. But a couple of points that I would like to mention here is, in green, I have indicated the area under the hysteretic curve, and it will be a very nice idea to start correlating this to our physical picture. Remember, in our physical picture of the double W-shaped potential barrier, there were two stable states, the stable state 0 and stable state 1. This is corresponding to the two ends of the hysteresis loop. You see, you have a stable state 0 where the storage node 1 is 0 and the storage node 2 is 1. The other stable state is where the storage node 1 is 1 and the storage node 2 is 0, and the metastable state is in this transition region. In this particular transition region of metastable state, if the characteristics of voltage V of N1 reaches near the metastable state, a small push in either direction can change the value from stable state 1 to stable state 2 or stable state 0 to stable state 1. So as you can see, the butterfly hysteresis curve of a cross-coupled inverter, which is the heart of the SRAM cell, can be very physically or intuitively understood from this kind of example. Okay. Now we come back to the original question. Why do we have a memory effect, or as we will see in this particular slide, why do we have this regenerative feedback? To understand why we have regenerative feedback, what we will do is, what is the meaning of regenerative feedback? What is the meaning of regeneration? Meaning of regeneration is, if a system is pushed a little out of its stable state, can it come back? Can it return back to its original state? And we will see how this hysteretic loops that we have helps an SRAM cell return back to its original state. So for this, what we will do is, we will consider that we were in stable state 0, which is that the VN1 or the voltage at N1 was 0 and the voltage at N2 was VDD. This is indicated by this solid yellow dot. Okay. To this scenario, what we are going to do is, we are going to add some extra delta V noise. Okay. We are going to add this extra delta V noise, and we will see if the system is capable of handling this noise. What does handling this noise means? Can it overcome this noise and return back to its original position? Then only it is a memory. Then only it is able to remember things. Okay. Important to realize that this delta V is lesser than the noise margin which is added to this stable state 0. Now, noise margin is a very technical term. In this case, we will say that this is a small disturbance. What is the definition of noise margin? We will see very soon, both qualitatively and quantitatively. But I am just introducing this term, which means that I am applying just enough noise such that the bit does not flip. In this kind of scenario, what happens? So let's analyze this using these inverter configuration and the butterfly loops. So in this case, since VN1 is the input and there is a disturbance at the input, it is but natural that we should look at inverter 2. Why? Because the input to inverter 2 is N1 and the output is N2. Since we have to consider what is happening at inverter 2 and we have color coded the two loops, we have to look at what is happening in the blue curve. Okay. So if the input is disturbed by delta V, what happens to the output? And that we do by projecting your input on the blue curve. So what we do is, we project what will be the corresponding output of VN2, and we see that the corresponding output of VN2 will be VDD minus delta V dash. Okay, just like there was an increase due to noise from 0 plus delta V, similarly VN2 will also get slightly disturbed by VDD minus delta V dash. Immediately you can see that the disturbance in V2 seems to be slightly lower in magnitude compared to the disturbance in the input delta V in the VN1 node. Okay. So this is the first analysis that we do. So what did we see? That a delta V change in the input caused a delta V dash smaller change, smaller lowering at the stable input Vn2. Now how do we find out, due to this Vn2 change, what was the corresponding effect in Vn1? There has to be a corresponding effect in Vn1 because they are cross coupled, right? So what is the corresponding change in Vn1? And to analyze that, we have to recognize the fact that for inverter 1, N2 is the input and N1 is the output. So because it is color coded in red, we have to look at the red curve. So let us look at the red curve, and this is what I have done. I have projected the input N2 on the output N1, and we see that the new position of Vn1 has now shifted towards the 0 point. And now you are beginning to see how by bouncing of the two loops, the disturbance is now getting mitigated. Earlier, the distance was large delta V. Now, this voltage or the disturbance is getting mitigated through this hysteretic loops. Okay. Again, we follow the same rhythm. We see that Vn1 has been changed. And because Vn1 has been changed, we need to project what is happening at Vn2 using inverter 2, which is the blue line. That is exactly what I am showing over here with my laser pointer. And you see that the disturbance delta V dash in Vn2 has also been mitigated. And within a few so-called bouncing offs of the hysteretic loop, you will see that the state both at Vn1 and Vn2 has returned back, has been regeneratively fed back to the original state without any noise. And this is the core reason why there is positive regenerative feedback in the hysteresis loops. So this is a very important concept. So very quickly I'll give you a recap. Very simple. You added a small noise on Vn1 and you saw which is the corresponding loop to find out what should be the value of Vn2. It turned out to be the blue curve, and you did it successively bouncing off curve blue and curve red, and you saw that just within a few bouncing of the hysteresis curves, you see that the value of Vn1 and Vn2 has been restored to the original values. So I hope this gives you a very strong feeling for why the SRAM cell has this so-called self-healing or regenerative feedback. However, it is very important to note that all this regenerative feedback is not infinite. The noise margin is not infinite. If you push the system out of some stability point, just like try to recall the W-shaped curve, within the height of the barrier, if you disturb the system, you will be able to regeneratively feedback. What I mean essentially is, if I disturb this system only till energy value less than EB, it will roll back after a few bouncing and come back over here. However, if I disturb it beyond the metastable point, there is a chance that the value will flip. And this is what we will see in the second graph. So what we have done is, remember this was the metastable state. Now the noise that has been added is more than the noise margin. So if the noise is more than the noise margin, we will use exactly the same rationale. If Vn1 has been disturbed, we have to look at inverter 2, which is the blue curve. And after a few bouncing backs of the blue and the red curve, you will see now the bit value has flipped, or the state value has flipped. From 0 state, you added a large enough noise, and now it has flipped to the new state. Okay, it has gone to the second stable state. From stable state 0, Vn1 has reached stable state 1. Okay, and both these things are very important. Right at the beginning of the lecture, we discussed the height of the barrier or the point of metastability needs to be designed very carefully so that there is some reasonable amount of stability to noise. However, it should not be so high that flipping the value, which is important for write operation, is also maintained. Okay, and this gives you a very good idea or understanding of what could be the definition of noise margin. We are looking at the qualitative definition of noise margin now. Later on, we will quantify it. Very simply, what is noise margin? It is the maximum allowable disturbance into the internal storage nodes that can be corrected by the system. If you cross the noise margin, the value will flip, the stable state will flip. If you are within the noise margin, it will be able to regeneratively feed back and restore your original value. Okay. With this, we will discuss the last thing that we want to cover. And with this, we are transitioning to the different operational conditions of the SRAM cell. And the simplest operation condition is that of hold. In hold condition, whatever the values on N1 and N2 are, stable values on N1 and N2 are, you just want to hold it or you want to protect it. It is very logical to understand that this can be done very easily by protecting the values or decoupling the values or the storage node N1 and N2 from the outside environment, which is nothing but bitline and bitline bar. You need to isolate N1 and N2 from bitline and bitline bar respectively, and that can be done by turning off PG1 and PG2, right? So if you want to turn off PG1 and PG2, which are NMOS transistors, of course, at the gate, you have to apply zero voltage, right? You have to apply a logic 0 at the gate, and that is what you do with the word line. So if the word line is deasserted or 0, that means N1 and N2 values will be protected. It will not be disturbed by whatever you are doing at bitline and bitline bar. I hope that makes sense. But here, what should be the value of voltage at bitline and bitline bar is also a very interesting question to ask. Should it be 0? Should it be VDD? Does it matter? That is the question I want to pose in front of you. And the answer actually is quite interesting. It is that bitline and bitline bar are generally kept floating. They are generally kept in floating condition. So you may ask, what is the rationale of keeping things in floating condition? And if you know a little bit of transistor physics, you will appreciate, although transistor PG1 and PG2 is off, real life transistors do not go to absolute zero current in their off state. They have a sub-threshold leakage. Sub-threshold leakage means in less than VG less than VTH, current does not become zero. It exponentially becomes lower for smaller VG less than VTH. Okay, so always there is a finite leakage current which flows through these transistors. Now, if you do not keep bitline and bitline bar to some value, if you keep it to some fixed value, there will be a leakage current which will flow through this, right? And that is what you want to prevent. So what you do is you just keep them floating. So the reason for having bitline and bitline bar floating is to prevent sub-threshold leakage or off-state leakage during hold operation, right? So to summarize hold operation, the word lines are turned off by making word line go to 0. The pass gate transistors are off, and node 1 and node 2 is decoupled or isolated from bitline and bitline bar. Okay, this is the simplest SRAM operation. In today's class, we saw what is the core reason that these butterfly hysteretic loops give you positive regenerative feedback and is able to restore the values of the internal storage nodes of an SRAM cell if the disturbance is within the noise margin, right? Also, we saw what is the fundamental of hold operation. In the next class, we will begin with a very interesting topic. We will see how read operation happens in the SRAM cell. Thank you very much.